rather than to get the precise value, quantity value of age. Okay, so because the one reason for this is that actual nodes we know that it will be keeping change. Okay, so and because it is from the with more a great number of the individual devices, the different types of the devices, so that aggregate models that we are generally or commonly used in our analysis. So maybe two commonly used aggregate models. So the constant power and constant impedance. Okay, so we have learned in the previous lecture. So the complex power and expressed by the voltage and the impedance. And so this is the node models. And for the power generations, we also have the generator models. Okay, so the generators in our discussions, we will assume that it's a synchronous machines. Have you known about this?
Yes, synchronous.
The first one, how do you the non-synchronous and the synchronous machine? Yes, of course. So we generally assume that the generators in our lectures are synchronous. Okay. Okay, so except for the window generators. Okay, so why all the example generators in our classes is a combustion plant. Okay, so it's being used the coal to produce the generators. We are not discussing about the wind generators in our lectures. Okay, so the third something that we will use two different models for generators. Okay, so the steady-state models and the short-term models. Okay, so the differences is that in the first steady-state models, so the generators will be a constant power source. You can see as like this equivalent circuit. So we will get the specific voltage level of this voltage source match. For example, it will be 1 volt and with 0 degrees phase shift, and in all of our process or in our working conditions, in the different working conditions, this source is 1 volt. Okay, so they keep unchanged. Okay, so we put the steady state model, so the fixed voltage, and so this is the model we use for our following lectures, the power flow and the voltage sketch, and also a short term. And actually, so our lectures in this semester we might get the requirement to start these lectures. Our lectures, or the name of our classes in this semester is called the steady state estimation of the power systems.
Yes.
So that there is another thing that we call the transient state analysis. We call it as a very short movement, in average movement, how the generators, such as all the parts of the power systems, such as the generators and the nodes, how it will be changed. So we will learn it in another classes we call the transient stage analysis. Okay, so this is for the short term. So generator, so we have the possible time. You can see the time varying reactance, so that every parameters of these generators will no longer be a constant value. Okay. So the power flow analysis, the most common system is pure the power flow. So node flow, power flow is okay. So actually we need to know what is the power flows actually first. Okay. So power flow determines the power flows in network. So we will just to discuss different systems with different power flows. Okay, so the power flow is can only be discussed in the same network. Okay, yeah, because the network one, the network on campus, the power flow here is different with the other systems. Okay, so second one is that or the bus voltage and power range. Okay, so with this one we'll discuss later. Okay, in this lecture. So because we assume that we are in the steady state, so that the generator or the power models is a constant. Okay, so the power source is a constant value. So that power flow will be a non-linear model in our these two natures, and fourth is the state state -2. Okay, because we choose the state state model in our natures. Okay. So before we start, we need to get some preparation knowledge of our mathematics. Okay. So the linear is non-linear systems. Okay. So this is a function in the mathematical function. Okay, h. Yeah, it's linear because this is 2. You can say it's a coefficient alpha 1, alpha 2, with this 2 input value, mu 1, mu 2 is the 2 input value. Okay, so that this coefficient can be just to take out of these functions. Okay, and also the 2 input in one function is equal to the input in the same function, but multiplied with a different coefficient. Okay, so this we call linear system. Okay, or linear functions. Okay, you can see that the output we introduce that the proportional because you can say that different coefficient, right? But it is proportional because this one when the input increase, the value with this one increase, and also the whole functions will also increase. Okay, so we have to wait for the proportional to the input. And the second one, the principle of the superposition. So have you heard about this? The principle of the superposition? Yeah. Yes, actually, superposition is the response of the system. So it's could be a little bit different with the position in our previous lecture in the transformer, in the three-phase transformers. Okay, so in the reliabilities. Okay, so the superposition will be the response of the one system is the sum of the responses that be caused by each subunits individually. Okay, so the difference individually, the individual, the input, the proportional to the sum of the whole part, the output of the whole function. Okay, so we call the principle of superposition. So anyway, this any functions will make these relationships. We call it the linear system or linear functions. So this is one linear examples. Okay, right? Because the S1 as the S2, and we have to use the same coefficient. Yes, Cs1 as the Cs2. Okay. And about for this one, so the square of the sum of the S1 and the sum of the S1 and S2, okay? So that is not equal, right? Because the square of the S1 and the square of the S2 and the 2 multiplied with the S1 and S2, right? So it's not equal to this. And so that in our systems, you can see that some image will be linear. Okay, you see that resistor, inductor, capacitor, independent voltage source. Okay, so independent voltage source and the current sources are linear. You see voltage. Current is proportional to voltage, right? The current is proportional. This inductance is proportional to the voltage. But also is also proportional, right? But this is the reciprocal of this current. But however, it's also the linear relationship between the capacitor and the voltage. Okay, so that the superposition learning. Okay, so this is for the linear. Let's say the resistor, impedance, or maybe this is the inductor, and this is the voltage source, the independent voltage source. Okay, so that way we call the linear system with a linear element. But for non-linear power system element, you can see the constant power loads, generator injections, non-linear, and since this system we cannot analyze by our previous or by the methods from our previous lectures. Okay, let's see, this is the constant power load, right? But this is not a resistor, nor the inductor, nor the capacitors. Okay, but this is a constant power load. We can say that you turn on an air conditioner. So the air conditioner here will consume 1 kilowatt per hour. So this is called a constant power load. Okay, so the power consumption is the constant value here. And such that because the power, you will see that power is not linear element, right? Right, this is the non-linear systems, okay? So that's in order to analyze or to solve the problems of the non-linear system, so we do the interactive approach. So you know the interactive, right? Interactive, right? Maybe several steps. The first step, we are approaching the true value, and second step, we are more approaching, and the third step, we are more and more approaching. So, okay, so the reactive approach, okay. So this is the mathematical examples, okay. So multiple solutions, all those solutions. So the first one. This is the curve, okay? So the square of the x is equal to 2, okay? So that because we're getting the solution to match this function is equal to 0, okay? So you can say that this 2 is that square root of the 2, and get a square is equal to 2 minus 2 is 0, okay? So that here we have the 2 solutions, okay? But how about this, right? Because actually in the real number part, okay, in the real world, square of the x were no less than 0, okay? So this value, the positive or the 0, add 2 equal to 0, right? So it's actually the solution of this function should be the imaginary number, okay, imaginary number I, right? But in our real world, so you can see that the topic is not here, and there is no such interaction point with this x-axis, okay? So there is no solution. Okay, so we assume that we are get the real solution. We are not considering the imaginary solution, okay? So that is the solution, we have no solutions. that we're working with these examples in our electricity analysis, okay? So we assume that it's a 9 volt DC, the direct current system, okay? This is the voltage source with a 9 volt, okay? And here is a PM condition, okay? So maybe I can change the not assume such as our laptop, okay? So 80 watt. So my laptop will need a constant 18 watt power as a supply, okay? Right. Also here is a resistor for 1 ohm, okay? So this system,
this current is 9 ampere.
yeah, 9 volt, 1 ohm,
So 9 ampere. And
it's of course a non-linear, right? Because this
is the 18 watt.
node we asking for a constant power consumed, right? This is not a resistor, this is not impedance, not an inductor or a capacitor, right? Okay, we can see that the power here is the current, the square of the current, okay, the current multiplied with the resistor or impedance, okay, impedance here, okay, so here we assume that the only, because the 18 watts is the active power, so this is the resistors here, okay. See the resistor of the node of my laptop multiplied with the square of the current, right? And here for because it's 9 volt is applied to the resistor here and the resistors in my laptop, okay? One is the R of my laptop and the nomenclators here is 9, okay? Square of this is multiplied with transistor is equal to 18, okay? So this is equation, right? So if we solve it, we can get 2 solutions. So the resistors of my laptop can be 2 or the half ohm, okay?
Like also for this current, sir. If I use I equals 0 over R, so these 9 are wrong, so I equals 9.
Yeah.
And if I use P equals VI, P equals VI,
Yeah.
so I equals P over 9.
Yeah, it's of course.
2 ampere and one is 9 ampere.
Yeah, it's of course because we have 2 solutions,
Yeah.
just as the examples here, okay? So because this is a curve and this substance in this shape, okay? So there will be 2 solutions
So it's not
here, but we also produce a nonlinear, right? For the linear system, there will be a very direct or straight line, so there will be only 1 solutions for the linear system, okay? Okay, so we'll start to establish our analyzing model, okay? So the first step, we're going to start a Barnes admittance matrix or Y. So what is the admittance? You heard about this? Admittance? Yeah, admittance. Why?
Barnes admittance matrix.
Quite easy, reciprocal or V, okay? Okay?
Yeah.
The inverse of the impedance.
Like conductance.
Yeah, sparse admittance is might more frequently used in our analysis. In our following lectures, we'll start to study the power flow. We'll use the admittance matrix. But if you are interested, you can find the solutions or how to calculate the power flow by the impedance matrix. It's much more complex. So that's this one is maybe much more easier. It's one of our advantages here, okay? So the first step, okay, we need to calculate the power flow. So the bars, so the impedance matrix, here we need to establish, okay? So this matrix is used to describe the structure, the topologic structure of this power system. Okay. So in this admittance matrix, okay, so many contains information or the relationship between all the bus current injections. Okay, the current and the bus voltage, right? V and I. So we're including these two, the information of the two parameters. So we use the KCL. So you know the KCL?
Yes, sir.
Yeah, KCL, right? That you have learned in the security theory.
KCL, KVL.
Yeah, KCL in the KCL laws to establish or to build the admittance matrix. Okay. Okay, so here is our brief graphic presentations with the generators, and here is the nodes, right? We're seeing nodes will be must 1, 2, 3. There will be 3 power flows here, okay? And we for the nodes, the buses, okay? So you see the buses and with the voltages, we coordinate the bus. The bus is actually we also coordinate the nodes in our power system, okay? And also the links between the different buses is like this, okay? Transmission line is used to transfer or to send the power flows, okay? So the power flow flows here, okay? And also, so this you can see the transmission line here. And finally, the nodes, the consumers, right? It actually has 2 nodes here, one here, but also we assume that here is only 1 node. And we give some specific values. So the 10 gigawatt, the 7, the 3, okay?
To balance.
Right, to balance, right? Okay, so here is the graphic representations. And we should be basement of our following description or following discussions. Okay. That transmission line, admittance, Y. Admittance in different transmission line, right? 1, 2, 3, 4, 5. So there will be 5 admittance. Right? And the inverse of impedance Z is like this, okay? So equal to the Z is equal to the resistor, we add the reactor, right? Reactance here X and resistance R here. So we have learned in the previous lecture, and for the admittance Y is equal to the conductance and the susceptance, okay? Conductance is the real part and susceptance is the imaginary part, okay? So very similar to the impedance, right? And the reciprocal of the impedance Z. And our real world, so the conductance is generally positive. However, for the B, the susceptance, so there will be the positive for the capacitor and negative for the inductor, okay? So, if a transmission line is connecting from the bus I to bus K, that from bus 1 to bus 2, we coordinate the Y12, okay? From the bus 1 to bus 3, Y13, Y14, and for this Y2 for right. Y3 for right. And please do pay attention that Y12 or Y121 is different variables, okay? 1 to 2 or 2 to 1. in some conditions, these two are equal. In some other very extreme conditions, they are not equal. Okay, y12 and y21. Okay. So the distance y t from the node I to the t, right? Okay, so the example is per unit y1 minus 4 and j, right? And if we would like to describe the third admittance, we call this yii, right? From the box I to the box I. But by indicates, right, acceptance for any shunt element to ground at box I. And just to imagine this. This is the A, B, C, right? And for YAA, the admittance, the third admittance of the bus A is that when we get to grounded, the other nodes, and what we call the shunt, right? The shunt element, right? Yeah. When we get to grounded, the all other nodes other than the package box, right? C the grounded, B the grounded, then the admittance from the bus A to the ground is the YAA. Okay? Yeah, we could reserve admittance, right? Because YAD we can easily convert easily to understand that the impedance the admittance from the bus A to bus B is here. Okay? But for the YAA grounded or other buses, and then you can calculate the admittance from the A to the ground. Okay? So no problems here.
Okay, this is per unit. IT.
Yes.
YIT.
YIT equals the mutual admittance. Okay, and this will be discussed, introduced again in the following page. This is mutual. If the I is not the T, is not equal to T, right? A, B is the admittance here. A, C is the admittance here. Okay? So this mutual admittance is very easy to understand. However, for the third, right? Third is that to grounded, and you calculate the total admittance from this bars to the ground. Okay.
So, about this equation we know when this is positive. This is positive for capacitor and negative for inductor. So this is negative, so this is inductor, so this is conductance. So conductance, and I convert it resistance, and this is I convert to inductance. So R equal 1 or 6. So
this we cannot do this to
so on by Y.
yeah, and then it is equal to the impedance. We cannot have two separately, okay? Okay, so we define that the Y bars matrix, okay, so here's the Y element. Well, element will be called diagonal element and off diagonal element, right? And for this, quite easy, right? YAA, YBB, Y and CC, right? You can see that for the diagonal, is the third admittance branch, and for the other part, the off diagonal is the end range with the deep range, right? Because you can see it's A, B, C, A, B, C, right? Is the diagonal, the third admittance. The off diagonal is a neutral because they are not in the same, right? Not in the same nodes. Okay? So that you can see for the third, we know that grounded, so that for the third admittance of the bars A is admittance of this bars A is the other, you can see that or the other admittance that connected with this bars, okay? For this you can see that is YA and Y2, Y2 and YC, right? Because this is the admittance of this bars and or the other bars which is connected to this bars and the admittance, the sum of the admittance, okay? And for the off diagonal bars, you see that because this is the direction of this you can see that the current, okay, the injection current from the A to B, so that we assume that this is a negative, because we assume that this injection is a negative, and this is based on the description or definition, okay? So the negative, we use 9 admittance, so that the future admittance from the box A and box B is equal to the negative 9 admittance, okay? And for box A, you can see this, we assume that this is 9 admittance, okay? Transmission line. So YA is what? Y1 is Y2, right? Because these two is connected and Y3 is does not connected to the A. And for the YAB is negative YE, right? So that is the diagonal element and the off diagonal, right? So that's why we call the admittance matrix and describe the power grid topology, right? Because you can see that for this we know that the Y3 is not connected to the box A, right? Because the box A YA is only equal to Y1 and Y2. Okay, so the power grid topology and the admittance, we know that Y1, we know that Y1 and Y2 is the specific value of this line admittance, okay? Also, to see just like this. Okay, so in our examples, we have the 3 buses, but if we have the 4 buses, see that this diagonal, right? This Y1 is called the serve, maybe the admittance in the bars, okay? Admittance in the bars. And Y2, Y3, Y4 is transmission line or the admittance, okay? Just like this, A is equal to this, the sum of 3. The serve, the admittance of these bars, right? And these 2 is the transmission line admittance, just like this. So the Y1, Y3 is the serve, and the connected transmission admittance, right? You can see that it's the same diagonal. And for the negative, for the mutual, right? With the Y and the 2, right? So the negative Y to 1, right?
Y12 and Y21.
Why? Because this is the row, and it's the column slash, so that we, and generally we will push the row ahead of the column. Okay, so this is only the definition.
We also need it in cyclic.
Yeah, but you need to do the same with most people do. Okay, so that in that case, everybody will have to do more video understanding between each other. Okay, so understand. So have you any questions about this? How to build a Y-bars matrix? Okay. And also we just different real and imaginary part, the compartments, the subset techniques, okay? Okay, so I'll show you one example, okay? So for the system, so we need to build bars with the admittance matrix for this work, okay? So the current injection in each bars is the difference between the current injection into the bars from generator and the current flow into the nodes, okay? Okay, for this you can see the bus 1, bus 2, bus 3, bus 4, okay? And here is the nodes, right? Is the arrow is the nodes, and for here is the generator, okay? So it's a cycle generator nodes. So if you use the testing KCL, right, the generator current in minus the current out. Okay, so it's equal to the I1. Yeah, I1. So I1 is equal to the I12, I13, right? I1, I12, I13 because the both 2 and 3 is connected to the I1, right? I can say that I12 is V1 minus V2 and divided by the impedance here, okay? Impedance A here, okay? So that because you can see the generator, the current is from here to here, right? So V1 minus V2, the difference of the voltage divided by the impedance here. See A, C, and the conditional A. And we use the admittance, right? The reverse of the impedance is the admittance, okay? So we can get this. And we have to put the same parameters together, okay? So here is the expression of the I1, okay? So similarly, the I2 is equal to 2-1, 2-3, and 2-4, right? You can see I1 here is the generator, so that T is sending out the current. So that's why here is 1, 2, and 1, 3. And for the 2, here is the node, right? The current flow in here, okay? That we will do 2, 1, 2, 3, and 2, 4, okay? So the differential order with this, okay? I1, 2, and 2, 1, okay? Because the voltage 2, 1 is here, we use this 1 minus 2, okay?
2, 1, 2, 3, 2, 4. Can we give?
See that because this is the generator orange minus the node orange, right?
Coming current minus going current. This figures are I need to see. So node 2 is 1 is coming from generator and from generator 3 to 2 to 3 plus 2 to 4. Sir, I24 I don't understand. How can I do?
I21 and I12.
I24, this third one.
I2 negative 4, because this is also a generator, right?
This is coming for load.
Yeah, it's coming for nodes, because there's no node here, and here is a node here,
Oh,
right?
understand, sir.
Okay, so this generator, so all the three are sending the current to the bus 2, okay? So that we can get this. And we also, we will repeat our steps, the steps from the bus 1 and bus 2. So the relationships with the current equal to the voltage, but particularly the Y bus. Okay, 1, 2, 3, 4. We see that the Y A and B, right? You can see that the serve admittance Y. This is the bus A, right? Let's see here is the A and B because here is the connected with A and B, right? YA and YB. And for the bus 2, A, C, E, right? Because there is 3 transmission line connected to the bus 2. And for the bus 3, it's C and D, right? And for the bus 4, it's only one, yeah, YD, the limits of this YD, right? And for the mutual, so this is from 2 to 1, right? From 2 and 1, so it's the negative admittance of the A, right? So we know that. But for this, the bus 4 and bus 1, you can see bus 4 is here, bus 1 is here, no connections, so 0, no connection. So make sure that everything here, except for the serve admittance of the bus admittance, every other part, the admittance will be 0. As long if there is no direct connection between, okay? The 0, you can see that the 3, 4 and 3, right? You can see that 4 and 3, because they are not directly connected, because they are connected to, but they are not directly connected. So 0, okay? So 0, right? So that it should be a symmetric matrix, okay? It should be the symmetric, and say 0, 0, 0, 0. There should be a symmetry with between the two sides of the diagonal, okay? Okay, so in that case, because the symmetry is a symmetric matrix, E is here, right? Let's say that bars KL is equal to the bars LK, right? Let's say the bars 3 to 2 and bars 2 to 3 the same, okay? Let's say this is a symmetric. Okay, so there is no any problems here.
No problem.
Okay, so we're through the following part. Okay, so as we discussed in the previous, the serve of the admittance, right, is equal to the sum of the admittance of all devices incident to the bus K. Okay, so the OR line that is directly connected to the bus K. Okay, so you need to add all of the 9 admittance. Okay, it's the third admittance, and for the off diagonal term, so equal to the negative admittance between the two bars, is okay. So that in that case, if we have a very large scale systems, maybe the network in board CT, okay, so there will be the sparse matrix. matrix. Matrix is like maybe there will be so many, maybe so not much connection between the different nodes, so there will be very maybe many zeros in the matrix. Okay, like this. Then here is the 4 zeros, and in a large matrix, in a large power networks in our real world, it will be sparse. Okay, the sparsity maybe is a numeric digits. Okay, finally the short term will be in the equivalent pi model. We're only find diagonal terms. Okay. If you are interested, so this change system is introduced in the lecture 7. Okay. So if you are interested to get a quick read or view of this, okay. So in the pi, let's say it looks very similar to the pi, right? Pi signals. Okay, so we are not just going through about this, okay? But you can see we can use the conclusions here directly, okay? The current I here, right, is the current, is the voltage differences between the voltage difference between here to here, right? Vi minus Vj and multiplied with K, right? And here is the current, right? The current Ij here is one part of the current is going through the Yk here, and one is through the capacitors here, right? Current will be divided into 2 parts, and here's the first part, right? I, the difference of the voltage.
This is the voltage drop of Yk.
Wow, it's too small. So I'm actually doing that. This part, the current here, right? The difference of the voltage not first with the admittance. That for this, you can see that here is the admittance, right? Admittance, and multiplied with the voltage, because the voltage is expressed as Vi, right? Voltage here. So here is the I, or the expression of the current. Here the box I, right? Current box I. And so for the third admittance of the box I, refer to the admittance from the other lines is the Yk, and for this, right? And so we use the inverse of the admittance, inverse of the impedance here to express it by K. Okay, so I'll take one example. Assume that the computing, the capacitors here is 0.1 J, and the impedance is here is the value, okay? Let's say, and for the I1, the current, right? Voltage difference between the two nodes of the voltage and divided by the impedance, and A is the voltage here multiplied with the admittance of the capacitor, right? Okay, for Z, and please do pay attention that this is the impedance, okay? That is not the admittance. So if you are doing your homework or your examinations, do pay attention that you need to take the inverse or the reciprocal of this impedance Z at first before you start your calculations, okay? This and then the impedance of this 12 minus 16, right? Y matrix, how this term A come from? 12 minus 15.9 J. How to calculate this?
For node 1 and node B, sir.
So this is the diagonal. This is the third.
Yeah, this is the diagonal.
Right, how to calculate? Because there is no bars of admittance, right? There's no bars of admittance. So you only need to add the line of admittance that will connect to the edge, right?
So 12 minus 16 plus the Z 0.1.
Right.
So we can write 12
Perfect.
minus
Right.
15.9.
Right. And for the neutral, we get the negative, right?
Yes, sir.
Negative, and it's also the same. Okay, for this, it's also this is this. Okay, so it's quite easy, right?
Yes, sir.
Okay, so using the Y bars, okay. So if we know the admittance matrix, the bars matrix, and voltage, we can get the current. And if we know the current and the Y matrix, we can also calculate the voltage, right? So that why we will need to establish the admittance matrix before we start to calculate the power flow, okay? Okay, so here's one examples. So assume that in the previous in this system, okay? So this is here the voltage, the voltage I, voltage J, right? So we can calculate the current. We can use this, okay? The current is equal to the voltage multiplied with the Y matrix voltage to this. So you know that how to calculate this, right?
Yes, sir.
The multiplication between the matrix. Okay. Okay, so we can get the current, right? The first one is this, actually this is this, actually this, right? There is a current matrix,
I1, I2.
so that is the complex power, okay? So conjugate of the current,
Yes, sir. I1 and conjugate of I2.
conjugate and use the voltage, we can get the complex power of the each bars. That's why we need to establish the Y matrix here, okay? Also, if we know the current, then we can get the the similar method, but inverse of the matrix multiplied with the voltage is equal to, multiplied with the current equal to the voltage. Okay, so here's the questions. So can you do you know how to calculate the inverse of matrix?
I use this step.
Yes, of course.
And I know this handwriting, but
Handwriting
it's
is
a long time. Let's take time.
handwriting maybe is a little bit. I will give you one. I will just to introduce one method, okay? But you can, of course, you can use your calculators, okay? So this will not require. So right, you know this. Here the unit matrix is matrix A, with the inverse of the matrix.
Yes, sir.
Okay. So E is equal to the 1, 1, 1. So the
One.
Yeah, and
Yeah.
of that row is 0, okay? It's like 1, 2, 3, 4, assume that, okay? So that we assume that the inverse of A is A, B, C, D, equal to, okay? A, B, C, D, right? The first one, A to C, 1, right? The first row, first column is the first, and the first row and second is 1B, 2D, to 0, right? The second row, the first column, 3A, and the 4C equal to this. And the first, second row, second column, right, 3B, and 4D is equal to 1. 4 unknown parameters, 4 equations. Then we need to calculate the A, B, C, D, and the alternate. But make sure there is some other more complex methods, but they're more easier to calculate. However, examinations, I think I will give you maybe at most 3 range matrix, okay? You get most 3 row and 3 column, right? So if you need to calculate, it's okay in your hand. Of course, if you wish to use your calculator, it's also okay. Okay? So that we'll start our power flow analysis. So before we analyze a power system, we do not know the complex power voltage and the current, okay? And sometimes what we know is that the complex power being consumed by the nodes and the power being injected by the generators and the voltage magnitudes. So therefore, okay, so we will need some preparations before we start to use the Y matrix equations, okay? Okay, here's some preparation. There's equations in preparations, okay? The TCL, right? We know that for the bars I, right, in the N, because we will assume that there is N bars system, okay? The current injection IA, right, here is equal to the current flow into the network, okay? The current I here is equal to the current flow into the all other connected bars, right? Right? You understand it? Okay? And since we can use this, the current equal to the Y, and first with the V, right? That the current equal to the sum of the multiplication of the admittance and the voltage, right? And then we can get the net complex power, okay? So V and I.
But circuit theory, we just do it without complex side, like I equal ZV, conductance and voltage.
Yeah.
But here is I equal YV.
Because Y is the inverse of the V. Just like I is equal to the V divided by the impedance Z. Right?
So, I mean this part we doing like real part plus imaginary part. But in circuit theory we just do it real part.
Whether there is an imaginary part, it depends on the network we are analyzing. So there will not be a general description of this.
Yeah.
But for this is a general description. Yeah. right? Let's have the break.
Yes, sir.
With these two lectures, there might be a little bit difficult.